So welcome to part 3 of lecture 29. So our goal in this part is actually to prove the Gram-Schmidt theorem. Okay, and so we might have sketched out the proof in Math 1B03, but here we're going to actually go through all the details about why it's true. Okay, so let's go to the start of my proof. And what we're going to do is we're going to be doing induction on J. And so it's kind of like what I was just saying in the last part is we're just going to do it kind of one vector at a time. So we're going to show if you had one vector, then you can do it. If you had you start with two linearly independent vectors, you can do it, and so on. Okay, so let's get going. And so the base case is quite straightforward. So for the base case, okay, we have that the norm of E1 is equal to 1, and the span of E1 is equal to the span of V1, since E1 is a scalar multiple of the vector V1. Okay, so just let me move back over so you can see what I mean here, right? So notice that E1 this is a number, right? 1 over the norm of V1 times the vector V1, so it's a scalar multiple of V1. So that's how we get the span of these two vectors are the same. And the norm of this vector, right, because we're dividing it out by the norm of V1, when we take the norm of this, this will cancel out the norm of the V1, and so we get the norm of this vector is 1. Okay, so the base case is straightforward. Okay, we kind of cooked everything up. Now what we're going to do is assume that whenever we're given j minus 1 vectors that are linearly independent, we can find E1 through EJ minus 1 that are orthonormal, such that the span of these j minus 1 vectors is equal to the span of the j minus 1 Vj, the span of the j minus 1 vectors V1 up to Vj minus 1. So this vector here, Vj, is not in the span of V1 through Vj minus 1 because Vj is the vectors were linear independent, so it means it's not in the span of these vectors here because these are the same subspace. Okay, so what we can do is we can take the norm of this vector right here. Okay, and this does not equal 0. So let me kind of explain why it doesn't equal to 0. Suppose that it equaled to 0, well that would mean that this vector here would be equal to this vector Vj. Okay, but that would mean that Vj is a linear combination of E1 to Ej minus 1, which is not allowed. Okay, so this thing doesn't equal to 0, and this is the denominator of Ej doesn't equal 0. Okay, so what that means here, what we're just checking here is that we're not accidentally dividing by 0 right here. Okay, so we're not dividing by 0 here. And the other thing we should see is Ej is defined by taking this vector and dividing it by its norm. And whenever you take a vector and divide it by its norm, you're making the resulting vector have norm 1. Okay, so we have that this vector here has to have norm 1. Okay, so i.e. has the correct norm. Okay, now what else can we have? What else do we have? Well, the other thing that we have is, so these vectors all have the correct length. We now need to show that they're all orthogonal. So let's take Ej and compute its inner product with Ek. Now Ej is defined to be the vector Vj minus the inner product of Vj E1 up to Vj ej minus 1, the inner product of these two elements, and times by the vector ej minus 1, comma, ek. And what I'm going to do here is there's actually a denominator here, right? There's some sort of constant, but I'll just write star for the denominator. Okay, so that's just some constant, just so I don't have to rewrite it all. So there's some giant constant at the bottom here. Now, if we use our products of inner product spaces, all right, so we can use our properties of inner product spaces and combine all of these things. So this term, the ek and the vj give me like vj over ek, and there's some sort of constant floating underneath of this guy. And over here, when we do the ek with the inner product of any of these guys, because ek is orthogonal with all the vectors that are not equal to it, it kind of kills off all the other terms. So you're going to be left over with vj ek, and we would have this big constant term right here, right? So it's not quite here. Let me fix this up. You would be left over with vj ek, comma, ek, and this would be all over star, because there's a lot of cancellation when you expand it out and then you collect the terms. Now, this guy here, I don't know if I left myself enough room. This is equal to, let's go to the next page. This is equal to vjek. And remember, there's just some sort of giant constant under there. And we're pulling out the vjek where there's a giant constant under here. And then this would be ek, right? But this number right here is 1, so we're subtracting the same thing, so this is equal to 0. Now you may need to get your own paper and pen out here and kind of follow through what I did here to kind of convince yourself that I didn't skip any steps. And to convince yourself that this argument is okay, that I pulled everything out and that I haven't destroyed any of the numbers. So, so everything works out. Okay, so you just kind of pay careful attention to where all of your numbers are. So the point is, at this stage, is that we now have the vectors e1 through ej is orthonormal. Okay, and not only that, we note that vj is in the span of e1 through aj by rearranging the definition of the vector ej. So what do I mean by that? Let's go back. And here's the definition. And so remember, this is just one giant number under here, right? It's a giant number under here. So you could just put it under each of the vectors. And so on this side, you have vj, and then a bunch of vectors involving e1 through ej minus 1. And over here, you have ej. So you could push this vector onto this side and push the vj on the other side. And then you've written vj as a linear combination of the vectors e1 through ej. Okay, so that's why vj is in the span. And so that means that the span of v1 through vj is contained in the span of e1 through ej, because we know that v1 is in this span, v2 is in this span, and so on. The other thing that we notice is that both sides have the same dimension, since v1 through vj and e1 through ej are linearly independent. So they actually will both have dimension, j. So we have one vector space contained in another vector space. They both have dimension j, so that forces them actually to be equal. Okay, so the span of v1 through vj is equal to the span of e1 through ej. So what we've done, just to recap, okay, kind of our strategy is we've created these vectors, And what we've done is kind of like one vector at a time. We've made a new vector from our initial list of vectors. At each stage, we're checking that that vector is the new vector that we added continues to make our set orthonormal. So each vector has norm 1 and is orthogonal to our previous vector. And at each stage, we're checking that we haven't changed the space spanned by those particular vectors. Okay, so it's a complicated proof. Maybe at first glance, it's you might want to try sitting down and looking at a specific example using Rn and the dot product. But yeah, it's going to be a very useful result as we going to see in our last part of today's lecture when we talk about consequences.